Okay, 안녕하세요. Right, that's about that amount of Korean I know. So, so before I start, can I just have a show of hands? How many of us here watches Netflix? Okay. Right, cool. Thanks. So, my name is Chin. I'm a cloud solution architect with Microsoft Asia Pacific. So I've been a developer for 18 years. And the past few years had been around distributed technology. And the past couple of years, I've been involved in a few blockchain projects in the government and financial sector. I'm going to share some of my experience in this project here. Right, so, let's start with this guy. Right, so this is Whitfield Diffie. So Whitfield Diffie is a pioneer in cryptography, right? So why I was thinking of sharing his photo here today is this very interesting story where the world almost lost blockchain, right? So blockchain is built on top of public key cryptography, right? So back in the 70s, there was no public key cryptography, right? So there was only one way to really encrypt a message, right? So back in the 70s, Whitfield Diffie, he was sitting in his living room. He was trying to come up with a way to send a message from, say, Alice to Bob, right? So for those of you that are familiar with public key cryptography, you will be familiar with the usual names that are used to describe. But just bear with me for a moment while we start building on top of these building blocks. So Whitfield Diffie was sitting in his living room. He was trying to come up with an idea, a mathematical algorithm on how to really send a message from Alice to Bob when the Alice does not need to pass along the key that she used to encrypt that message to Bob. So fundamentally, Alice has a different key than Bob, right? So it might sound very obvious to us nowadays, right? We all know that, we just need a public key and a private key, and that works. But back in the 70s, this was not invented, and Whitfield Diffie actually came up with the idea. And when he actually came up with it, he thought of going downstairs to get a Coke, right? So while opening the fridge and then doing all the things that he do, he kind of forgot about the whole concept, right? So imagine he actually got it back eventually, but imagine if he never got it back, right? He forgot about it. So there will be no blockchain in the world today. There will be no public key cryptography. So amazing moments in the history of mankind. So let's go into a little bit of formal theory on blockchain before we move on to the commercial applications and subsequently the Microsoft offerings around blockchain, especially in the cloud, the Azure cloud. So what is public key cryptography? Fundamentally, in public key cryptography, we have the public key and the private key, right? So public key is something that you can give to everyone. You could even put it out on your Twitter page or your homepage or your Facebook. And your private key is something you keep for yourself, right? So here we have a scenario where Alice is trying to send a secret to Bob. So to do this, Alice will use Bob's public key and her own private key to come up with that secret, right? So that secret, it could be transmitted to Bob by paper, or it could be in an email, or it could be any form. It could be IM or whatever, right? Once Bob gets that message, it decrypts he can use Alice's public key and his own private key then to decrypt that message and actually read that message, right? So this is made possible by algorithms, right? Like the Diffie-Hellman algorithm, and subsequently, if you know, Rivest, Charmair, and Elderman, which formed the company RSA. So all of those, right, are enabled by this very simple concept of public key and private keys, right? So that's actually one concept to understand, to really understand how blockchain came about and how blockchain is really useful in providing that trust that it provides. Okay, the second concept that you need to really know on to understand blockchain is this thing called hash functions, right? Hash functions are really just a very simple concept, right? It takes an input and gives you an output, right? But what's unique about the output is that it's always of fixed length, no matter what kind of input you feed it, right? So here we have fox, we have a whole sentence, the red fox jumps over the blue dog, and all of this, right, it eventually ends up as a digested hash, right, which is of this length, right? The other thing that is unique about it is that most good hash functions are try to avoid this thing called collision. It is unique in itself, right? So collision is when you get the same hash from different inputs. So generally, for the understanding of blockchain, we get the same block, right, of the same hash block of the same length, whatever input we give it to. So the next concept will really bind all of this together, right? So currently it's still a bit abstract. So the next block is about digital signature, right? So digital signature is very relevant to trust. So today, when you buy a house or when you go into a business with somebody, you have a contract, right? And you sign it. So the moment you sign it, it becomes binding, right? So it means you have read through the content of the contract, and you agree to the content of the contract. So similarly, with digital signature, you agree that you have seen the data, and you agree to the content of the data, and you sign it, right? So how does this happen? Typically, you will have a string of data, right? It can be anything, okay? You take a hash of that string or that data, you encrypt that hash. So, okay, doesn't work. You encrypt that hash using your private key, right? And you attach that data and the encrypted hash along, and that becomes your contract, right? Or your digital signature. Okay, so that contract you can put it up anywhere you want. You could send it to a counterparty, and the counterparty can use that to validate your signature. So what do we mean by validation? So what that means is that, remember, the contract will always have two components, right? The raw data, okay, that you signed, that you agreed on, and the actual signature itself. So what happens when you validate, right, is you take the data, you pass it through a hash function to get the hash, and you decrypt that signature with the recipient's public key. The sender's public key, the signer's public key. And this is supposed to be the same, right? So when that's the same, you can actually be assured that nobody else, by way of mathematical truthfulness, can actually sign or have actually confirmed that he has seen this data and then he has agreed to it and he has signed it. Right, so those are the three kind of like mathematical or computer science concepts that are important in the formation of the blockchain. So how so? Here we are going to see. So blockchain And it's actual manifestation like Bitcoin, Ethereum, right? So it's actually based on the basis of the coin, right? And transactions, right? People passing the money, the value or the coin from one person to another. But how does this actually happen in actuality in the computer, right? So how this happens is actually by way of a transaction chain, right? So focus currently on this middle portion here. So this middle portion here describes the act of owner 1, right? Actually passing on that coin to owner 2, right? So how do we actually represent this in a data structure, right? So it's actually in this transaction chain. So what happens is, remember, the concept of the public key. So when owner 1 wants to send that coin to owner 2, it actually takes owner 2's public key along with a hash of the previous transaction. It signs it with his private key, and that forms that transaction. Okay, so because all of this is, as we have seen just now, mathematically proven to be truthful, the transaction is therefore non-repudiable, and that's where you get the immutability of the blockchain. When people say that blockchain is immutable, here's the mathematical concept that underlies that statement. So, the blockchain is then formed from many transactions being grouped together in one block, and that block is then hashed, and that hash is then placed in the next block, right, with a nonce. So a nonce is actually the result of mining, right? We will not go into the details of the nonce because it will then become a lecture more than a talk. So we'll move on. But that's how a blockchain is formed. So, and logically, right, if you look at the transaction, what is in the transaction is actually a very simple ledger, right? So then probably it comes to your mind now that I could just do this in a relational database. What's so unique about the blockchain, right? So because I could do that structure that I just mentioned in a relational database as well, right? So here's where the blockchain is different. That same chain, that same transaction chain, and that same blockchain is actually decentralized. It's distributed across many, many different members of the blockchain network. So these members can be stakeholders, or they could just be anyone, depending on the nature of the blockchain, right? So in a public blockchain, anybody can be a member. Anybody can say, I want to hold a copy of that ledger. And the person can be anonymous. So Bitcoin, Ethereum, you can spin up a server today and you can download that ledger. It will take you a long time, but you can do that, right? There's also enterprise blockchain, right? So enterprise blockchain is where we see a lot of activities in finance, and Microsoft had been involved in a lot of projects and proof of concepts in this arena. So there are two aspects of enterprise blockchain. One is within an organization itself, where different departments, they need to kind of like establish an ecosystem of trust. So this can be, say, in a hospital where there are different departments in charge of different aspects of the hospital that may want to, say, create an eventing blockchain, right, to really record events in an immutable and non-repudiable way. Or it could be within a consortium, such as the one that I'm going to describe soon, like a consortium of banks that may want to do interbank transfer. So, in essence, when any of these participants, they form a blockchain, they get 4 benefits, right? As we can see just now with the the central ledger owned by one relational database, there's the relational database itself becomes a central point of failure, a central point of truth, and that is in itself a risk, right? So generally in a blockchain, truth is established by consensus. So you do not have a man in high castle saying, this is the truth, right? What if that one is actually compromised? So that again is the resilience that blockchain provides against things like fraud, and somehow it becomes simpler and more efficient as well, because you might think that, hey, now instead of like one guy holding one relational database, I have 10 guys holding 10 relational database, and that is not efficient, right? But in practice, this is more efficient because the transactions that happen, say, in a federal bank, that same transaction is today actually held by the 10 other banks that are transacting with the federal bank as well, right? And these 10 banks, they do hold the similar amount, the similar data, and with their similar IT people and similar investments into their database systems, their firewall, and etc., right? So with the blockchain, these are more decentralized and more standardized, giving birth to the efficiency and speed that we will see. And all of this increases revenue and savings. So one project that we've been involved in last year around the blockchain, and like a lot of what we've seen earlier, where decentralization happens, is actually Project Ubin, right? So this is Project Ubin. Project Ubin started with actually forming a consortium, right, and introducing an electronic currency into the consortium, right? Then it moved on to actually grid lock resolution and liquidity savings. So these are the challenges that finance actually within real-time gross settlement actually faces. So actually, Project Ubin, led by the Monetary Authority of Singapore, actually has carved out this roadmap of development for Project Ubin. So let's have a look at phase 2. So in phase 2, it was trying to resolve this challenge called grid lock resolution. So this is not a new problem. So it's not a problem that's introduced by decentralization or blockchain. So it is an old problem since the beginning of interbank transfers. There is always this problem of gridlock, right? So what is gridlock? So gridlock is when such a scenario on the left happens, right? When Bank 1 wants to transfer 100,000 to Bank 2, okay? But Bank 1 has 50,000 in his account right now, in his bank balance, right? In his balance with the central bank, okay? So he can't transfer that 100,000 to Bank 2. So it needs to actually receive 50,000 from Bank 3 before actually being able to transfer the 100,000 to Bank 2. But it cannot receive that 50,000 from Bank 3 because Bank 3 is waiting for 130,000 from Bank 2 to have enough money to transfer to Bank 1. So in essence here, like nobody can, no money can flow, right? So traditionally, gridlock resolution can be resolved by an algorithm, right? But it needs visibility, right? So therefore, the role of the central bank. The central bank has a visibility. It maintains a system. In the case of MAS, the system is called MAPS Plus. It's been around since, I think, 2003, right? So in this case, MAS actually has visibility of all of these transactions that are happening between all of the banks. It runs an algorithm. The algorithm gives MAS an answer and the banks as well. So what needs to happen? eventually is that Bank 1 can just transfer 50K to Bank 3, and Bank 2 can just transfer 30K to Bank 3, and that's it, right? The gridlock resolved. So gridlock resolution is about this, right? So in a decentralized way, things become a little bit more complicated. So how so? Imagine decentralization, right? Without a central bank, we will need to do gridlock resolution, right? And the banks will actually emphasize a lot on privacy. Okay, so that middle tier here, the middle tier of this functional scope. So what do we mean by privacy? So if you go back here, right, Bank 1 and Bank 2 and Bank 3, they have all of these transactions happening, right? But Bank 3 will not want Bank 1 to know that he's waiting for 130,000 from Bank 2, or that it is transacting, it is actually needing that money from Bank 2, because this implies maybe that Bank 3 is not strong enough. So there's a lot of data points that you can get from full transparency, which is what a public blockchain like Bitcoin and Ethereum is, right? If you can run some big data analysis, you can discover a lot of interesting things. If you actually know who's behind that public key, right? So the interesting point with a lot of enterprise blockchain is concerns such as this, and Microsoft has the solution for this kind of scenarios as well, and we are building it and we are open sourcing it, and I will describe some of this effort in a short while. So for Project Ubin, this is completed around Christmas last year, and it involves three technology, blockchain technology: Hyperledger, Quorum, and Corda, and all of these are turned on a Azure subscription. So this is a successful project. You can actually get the white paper from MAS website. So the next aspect that is very kind of like very messy at the moment is trade finance, right? It involves so many legacy paperwork, right? So in a typical supply chain and trade scenario, there are typically at least 5 to 10 documents. There will be the letter of credit, there will be the purchase order, the sales order, the confirmed purchase order, the delivery order, the proof of delivery, and etc., right? And even like some customs form and all of this. So all of these things are very, in a sense, messy because it all involves paper, right? And paper, besides being very hard to manage, and it is also very prone to fraud, right? So at any one point, a paper can be, falsified. And this is a very big problem today, and there are efforts that Microsoft is involved in to solve the problem in trade finance. But let's take a look at what we could do without blockchain just to see the difference between a standard blockchain transformation and a standard digital transformation and a blockchain-based digital transformation, right? So this is what you get from a standard digital transformation, right? So let's take a look at this previous scenario. There are so many parties, 4 or more involved. There are many, many documents. So with digitization, with standard digitization, the 4 parties can actually use some form of digital transfer to avoid the need for paper, right? But what does that mean, though? With a standard digital transformation, there's a lot of investment that is required by each party, right? They will need to maintain the same layer, their own layer of data center, corporate network, web server, application server, database server. And they will need to maintain the people to operate this. In a blockchain scenario, they have one single standard, right? They maintain that. And for that, they get to be a lot more secure and a lot more distributed. And remember the point on digital signature, a lot of those documents, they are signed and recorded onto the blockchain.